Good evening. Hope you can hear me and see my screen. Great. So, not sure how many people will be joining, so let's get started. And to those of you who are celebrating, wish you a happy Ganesh Chaturthi. And welcome to the week 8 live session of the CS104 course. So, let's get started. I will skip this since I think all of you are kind of familiar with it. So let's start with the doubts from week 7. But again, since we are at the 2/3 mark of the course now, 8 weeks out of 12, if you have any doubts so far in all of the 8 weeks, please feel free to ask any time during the session. And either if I find time during the session itself, I will I will answer your doubts. If not, I will do it in the next week. Thank you so much, and thank you for joining in today. It would be very boring to teach an empty class, so I'm really happy that at least some of you have joined. So, okay, let's get started. So, we said we would discuss floating point numbers and the floating point format in general, right? So, I'm sure that, this standard is called IEEE 754, right? So, I'm sure some of you have heard of it, and many of you would have seen this sign bit, exponent and mantissa, right? The three sections of a floating point number. So in a standard FP32 number, this is what that looks like, right? There are 32 bits, 0 to 31. 1 is a sign bit. There are 8 for the exponent and the remaining 23 for the mantissa. Now, I have picked a kind of a blog post which explains this in a very accessible manner, right? What is the whole idea behind floating point? So I've linked it here so you can go through it, but we will also discuss this briefly and it will hopefully strengthen your understanding apart from thinking of this as exponent, mantissa and sign bit, right? So this is an alternate way of understanding the same thing, right? I just feel that it will help you understand it better. So let's see what it says. So the other way to look at this three division format is to think of this as a window and this as an offset, right? The sign repeat kind of remains the same. Now the window kind of tells you which power of 2 the number will be in. So here are some sample windows, right? 0.5 to 1, 1 to 2, 2 to 4, 4 to 8. These are all powers of 2. For instance, this one is 2 to the power of 2, 2 to the power of 3. So, since you have 8 bits for this, you can have buckets up to 2 to the power of 127 to 2 to the power of 128. This is the largest window you can have, right? Now this part of the representation, you can think of it as an offset. Basically it divides this window into a certain number of portions. How many number of portions is that? It is, remember that this is 23 bits, right? 0 to 22. So it divides this window into 2 to the power of 23, which comes out to be this, which is 83,88,608 buckets. Now using these two things, that is, one is kind of telling you within which 2 powers of 2 the number lies in. The second offset tells you, it kind of tells you in that from the starting point of the window, what is the offset from this value that you are trying to represent. Now using these two, you can kind of approximate a number. Now given that you have only a certain number of buckets, there are certain numbers you can't exactly represent, right? That's why we are talking about approximating a number. And the window is a very good mechanism to protect overflow. Basically, when you reach the maximum in a given window, you kind of roll over or float right to the next window. For instance, if I reach 4, I simply have to move to the next window, right? But now you have to realize that there is a kind of a trade-off here. So as you move to larger windows, remember that this number of buckets in a window remains constant, right? So if I am talking about very small windows, for instance 0.51 or even 24, in between this, which is 4 minus 2, right? These numbers itself, you can represent 83 lakh of them, meaning you get a very fine precision, right? Whereas if you go to a very high window, the higher your window size becomes, the lesser precision you have. So the trade-off here, and you will hear this spoken about many times, is a range versus precision trade-off. Range refers to kind of how much you can represent, right, in terms of what range of numbers you can represent, whereas precision refers to how accurately I can represent a number, because remember that we are only approximately representing a number. So it's like saying, let's say I want to represent 2.485, right? Now let's say I write it as 2. This is one level of approximation, right, where I've lost everything. I can also write it as 2. Maybe 2.5, right? Or if my window size is so huge, then I might end up approximating this to, let's say, 1 or something like that, right? You get the idea. I think we have more examples here, so let's look at this. So so for instance, let's say the number we are trying to represent is 6.1. So first thing is, between which two powers of 2 does it lie? 4 and 8, right? And the offset, if you have to visualize these two fields, the window represents this range between 4 to 8 for 6.1, and the offset is basically how far away from the start of the window, which is 4, is 6.1. Now talking about precision, this is what we were talking about just now, right? How much precision is lost when the window covers a wider range. So here is an example where the window is 1, 2, where you have the same 83 lakh something, right? So what is the precision of this window? It's basically the span of this range, which is 2 minus 1 divided by 83 lakhs, which comes to this very small number. So any number you try to represent in this window will be at worst this much different from the actual value. But if you take a larger window like 2048, 4096, this covers this window covers a range of 2048, right? Basically 4096 minus 2048. But what is the precision you get here? It is 0.0002. So you can compare this small value to this, right? So here, if I am trying to represent two numbers that are off by, let's say, 0.0001, they will overlap, right? So you lose that precision, but what you gain instead is this range. So you are not losing too much precision to gain this range. That's kind of the idea, and that's why that trade-off is okay. But what I would encourage you to do, since this is not very fundamental to the course, I am spending only 5 to 10 minutes in today's class, but what I would encourage you to do is take a few of these numbers and actually try to represent them, manually work out the math as to what you get for the exponent, how the sign bit works, and then what you get for the mantissa. That will help you even strengthen your understanding of this even more. Then if you have further doubts, we can still talk about it in detail. So I have not covered things like this, subnormal numbers, denormal numbers, and things like that. If you are interested in that, or you are unable to understand that, once you go through this blog post that I have linked here and you try out a few examples, let me know, right? We can always discuss more. But hope this clarifies. I think some people said that they didn't understand this whole idea of floating point, right? Does this help? Or is it more confusing? More confusing, I see. Okay, so the idea is, let's say I have a certain number of bits for the exponent, a certain number of bits for the offset. Let's say I keep that fixed, right? What would happen is my range would come down a lot and my precision is also fixed. Here what we are trying to do is we are trying to kind of get a better range, but you only have a certain number of bits, right? So to get a better range you need to trade off or give away something. What we are giving away is the precision of the number. But if this seems very complicated to understand, I think first go and look at just this representation, right, and try to work out a few examples where you take a floating point number and put it into this format, into an FP32 format. Then come back and look at this. Hopefully it makes sense. Did everyone else find it confusing too? Okay, maybe that's a yes. Let's see. If you still want a more detailed explanation of this, I can try and find an easier one or even work out those examples in one of the future classes, but let me know. I see, you get confused. Okay, so I think what would help, I'm kind of assuming that you guys have seen this representation before, that you see the exponent, mantissa and the sign bit, but maybe you haven't done that, right? So maybe I'll try to get a more basic example and then repeat the explanation of this. Maybe that will help. But broadly it is that idea. Actually what you can also do is to try and ask yourself this question, right? I want to represent floating point numbers and my idea is that they should be represented to a good amount of precision, right? You don't want to lose precision of the value that you're trying to represent. Basically, like I said, let's say I'm trying to represent 10,000 and your system, so let's say I propose one system, let's call this system 1, right, where my range goes from 1 to 10 lakhs. Okay, so this you might think is an okay range, right? Let's not talk about absolute ranges for now, but this seems like a good enough range. But if I tell you that the precision of this is just 0.1, now you might wonder what is the difference between 10,000 and 10,000.1. Depending on your application, this 0.1 might make a lot of difference, right? For instance, HPC applications, high performance computing applications, scientific applications, all of those, the workload depends a lot on getting very high precision. So you might see people using FP64, right, which is called double precision, meaning that you have a lot more bits for the precision part of it. Why is that? Because it's very, very important to the workload. So this is one system that I propose where let's say I can only have a 0.1 precision. Now I'll give you another system where you can represent 1 to 100 but with a precision of let's say some very, very small number. For instance, this one, let's say 0.00001, right? So this means that any number I try to represent in this system will have a very high precision. It will at most be off by this much. So when I talk about that difference, right, it is the number itself versus what its representation comes out to be. Let's say this is x prime. So x difference x prime is what I am talking about, right? So this is the precision in this system. So if you look at both of these, one of them offers you a very good range and not so good a precision, right? The other one offers you a very poor range but it offers you very good precision, right? So in a way, you want your number, your data format to be flexible, right? It has to adapt to both of these things. It can't be rigid and support only one kind of thing. That would result in multiple data formats and having to switch between multiple of them, right, depending on your requirement. So instead, what floating point format tries to do is to have this trade-off between the dynamic range and the precision. Why can both happen at a time? As in, let's say I have a very big value, right, that I want to represent accurately. That would be a case where both can happen at the same time. For instance, I might have 10,000.00001, and now I need both range and precision to represent this accurately. But that doesn't mean that I can take, instead of 32 bits, I can take maybe 64 bits or 128 bits. It has to still be efficient in representing it. So floating point format is kind of built to take care of all of these situations. Now, does this help a little? Or if you have questions, feel free to ask. Things like what you just asked, right? Why do both happen, or why is this needed? Ask those questions, don't hesitate. Any doubts, any questions? And interestingly, what I told about HPC applications, right, that they need a lot of precision, is not the case for deep learning applications. So they actually work with they can work with very low precision as well, which is why if we move to the next slide, right, you will see a lot of different formats. So FP32 was what we just discussed. It's called single precision IEEE floating point format. Now there is also half precision IEEE floating point format, which is FP16, which reduces your exponent and your mantissa, right? So you can compare the range of this versus this. You'll see that the range is much lesser. Now there are variants like bfloat 16, TF32. So these are all vendor proposed formats, right? For instance, bfloat was proposed by Google, or for mainly things that run on their TPUs. Similarly, TF32 I think was proposed by NVIDIA. FP8 was proposed by a bunch of people. These are all newer formats. So you can see that some of them, like bfloat 16, keeps the exponent, number of bits for the exponent, same as the single precision standard format, but reduces the mantissa. Now think about both, right? What happens to the range? What happens to the precision? So the range remains the same, which you can see here, but the precision comes down a lot, because now remember we spoke about this bucket and how many buckets would be there in one window, right? That number of buckets in a window is reduced, because now it's 2 power 7 instead of 2 power 23. Therefore, this one gives you the same range as FP32 but lesser precision. Now you might wonder, based on what I just said, right, why is that? So that's again what I was just talking about, that for deep learning workloads the precision doesn't matter as much. Even if you lose precision, even if you are only able to have 7 buckets per window, the final accuracy of the model is good enough, right? That's why. Now how does this help? Basically you're only using 16 bits, right? So your memory consumption first of all comes down, then your computations also get reduced, right, because your data itself is smaller now. So this results in a lot of benefits. Similarly, your TF32, FP8 is even more. FP8 reduces both the range and the precision, and it's found that that also to a reasonable degree is successful with deep learning. So again, you see now that the workload can change the format itself depending on the requirements of the workload. So pay attention to these things, right? When you see a new format, ask yourself what happens to the range as compared to its standard IEEE counterpart. What happens to the precision? And you have to look at the number of bits in the exponent, number of bits in the mantissa to understand that. Is this helpful? Okay, good to hear that. But if not, feel free to ask, right? Maybe today I can't spend more time since it's been 20 minutes, but okay, this helps. Great, good to hear that. But if you have further questions on this, ask, because this will help you beyond this course as well, right? Knowing these floating point formats fundamentally helps you understand how these numbers are stored. So if you have questions, for instance, what are these subnormal, denormal? I don't know if you noticed, but during this transfer learning lecture, right, you might have seen that graph. I think before the transfer learning, the mixed precision lecture, you might have seen this graph of values that are represented in TF32 and what becomes zero, what underflows and things like that. So go look at some of those things after you've understood this now. And if you further have questions, feel free to ask me. We can again spend some time in the next session. But we will move ahead. This was again something I discussed last time, but I think somebody said that they did not understand it very well, right? So a quick recap in strong scaling. So we look at this with examples today, and hopefully that will also help you relate to it better. So in strong scaling, YouTube channel link, sure, I can do that. I think this should take you there. Yes. Okay, sure, no problem. Let's come back to this. So in strong scaling, you're keeping the workload the same and adding more resources or compute to it, and you're expecting it to scale up, as in you're expecting a speed up, right? But you'll notice that the speed up saturates. Now here you're increasing the number of processors. What is not shown here is that the work also increases, and therefore it looks like you're getting a linear speed up. But what you should remember in weak scaling is that both the work and the number of processors increase. Now let's look at, again, this is taken from a blog. Sometimes I pick things from blogs rather than like a paper or something, because they're written to be easily understandable, right? But make sure you look at the source of the blog. For instance, this is from HPE. Sometimes there are also individual people like this who write these blogs, so make sure you look at the blog and kind of ascertain that the information is authentic or reliable in case you are looking for things on your own. But when I put these resources, at least I do a sanity check first that everything that's mentioned there is correct, right? So you can read this later. But let's talk about strong and weak scaling in the context of your deep learning that you've been learning about all these days. So like I was saying, strong scaling assumes that the problem size remains the same and we vary the number of computational devices. So now from a deep learning point of view, you can think of this as a batch size, right? You're fixing a batch size and you're increasing the number of CPUs or GPUs, let's say GPUs for now, to train the neural network. For instance, you're fixing the batch size to 1024 and you're adding GPUs. Now basically your first configuration was like this. You had one GPU of ID 0 and your batch size was 1024. So your effective batch size is the same as the per GPU batch size, 1024. Now I'm adding one more GPU, so the number of GPUs becomes 2. Let's say the IDs are 0, 1. Now I'm not changing the I'm not changing the batch size, right? I'm just basically, if you find this batch size confusing, think of it as the work. So I'm not changing the work, I'm only adding more GPUs. So what happens to the work per GPU? It gets halved. Each GPU will take 512 samples, but your effective batch size remains the same. Similarly, if I have 4 GPUs of ID 0 to 3, the per GPU batch size will be 256, but the total work done or the effective batch size will remain the same, right? And similarly here, if I add 8 GPUs and I change the per GPU batch size to 128, my total batch size will still be 1024. So strong scaling is when you do this, when you keep the problem size the same and you add compute resources to it and expect to get a linear speed up. Typically you expect to get a linear speed up, but in practice many times you will see it saturate. If you remember last week or the week before, there was that example, right, where we said one A100 does it in so much time, and then we said 4 A100s, but the time did not go down by half or did not go down by 4 exactly, right? That's kind of strong scaling. Now, if we were to talk about the same thing in the weak scaling format, what we do is we increase the amount of work, or in other words, the amount of work per device remains fixed. See, basically what I'm doing, I used to have let's say P processors. I'm scaling it by some factor n, right? In a very simple case, this is one processor to start with, it becomes n. Similarly, my problem size, if it was x, I changed the problem size to also nx. So basically here every processor was dealing with x. Now I have increased both the processors and the amount of work. So still every processor will be dealing with the same amount of work, right? So amount of work per compute device is fixed. That is another way to think of weak scaling. Here the amount of work, total amount of work remains the same. Here the amount of work per device or per processor remains fixed. So, but you're increasing the problem size itself, right? So here's an example. With one GPU, let's say you had a per GPU batch size of 128, your effective batch size is also the same. With two GPUs, now I'm keeping the per GPU batch size or the work done per processor the same. But because there are two GPUs, your effective batch size now becomes 256. And similarly, when I add 8 GPUs, 8 into 128 becomes 1024, right? So that's how this works, weak scaling. So now you're increasing the total amount of work and you're increasing the number of processors or GPUs, and you're expecting this to scale, right? You're expecting this to look like this. Again, will that happen? Will that not happen? There are some concerns. For instance, you will notice that the batch size itself changes, and from this lecture you would have realized that batch size is a hyperparameter and increasing batch size has a lot of effects on convergence, right? So again, whether this would scale or not is another question. But understanding what strong scaling and weak scaling means in the context of deep learning is what I intended this for. So hopefully the definitions of strong and weak scaling are clearer now. This is also a bit of an advanced concept, but it would definitely be useful to know this. Any questions on this? No, okay, good. So I think someone asked me for a revision of week 6 assignment questions. So I've put these in. So we'll follow the same format. I'll read out the question and you can tell me what the answers are. But the only thing different in this assignment was that your options were not radio buttons, right? As in there is one correct answer. That was not the case with all the questions. There were multiple questions, correct answers. So typically when you see a checkbox on the website, for people who have never seen this before, if you see a checkbox, then it means that there can be multiple correct answers. Okay, I see a question. What is the no with respect to? I'm just seeing your no, so I didn't understand what that was. What is the advantage of weak scaling? The advantage of weak scaling is that it's easier to achieve. So here, as you see, even if you have 5%, so here for instance, your parallel portion is 95%, right? Even then, the speed up that you can achieve saturates very quickly, right? It's 20. And notice how many machines I'm adding here. I'm adding 1024, right? So this makes it very difficult to achieve in most workloads in most cases, right? Strong scaling it's just an ideal notion, but most of the times it's very difficult to realize in practice. Weak scaling is a lot easier to achieve because of what you do, right? You're increasing the work, total amount of work, and adding more hardware. So that means that you won't have these bottlenecks to deal with, because your parallel portion is now being split across multiple things, and so this kind of doesn't be a bottleneck anymore, the sequential part. That's the whole idea. Again, I had an example in last week's slides. If you can take a few values of the sequential portion and work it out both in strong versus weak, you will kind of see what the speed up comes out to be. Okay. Was there any other question? I don't remember what the last no was for. I don't know if I asked something or. So we had just started discussing this assignment, and I was telling you that there could be some questions with multiple correct answers, right? And typically on a form you would see check boxes next to the options. That indicates that these have multiple correct answers. So let's get started, and then as usual you can tell me whatever you think is the right answer. We won't spend too much time on this because we have this week's assignment also, this week's model assignment questions to also go through. So we'll try to wrap this up in 10 minutes or so. Which of the following steps are involved in mixed precision training? Porting the model, ignoring gradient values, adding loss scaling, reducing the model size to alleviate gradient scaling. We have one answer saying A comma C. Okay, anybody else? A comma B, ignoring gradient values to speed up training. Okay. Any other answers? Okay, let's look at the answer. It was A comma C. So porting that, I think everyone got it right. Yeah, one more A comma C. Porting to use FP16 wherever appropriate. Then I think the confusion was between B and C. Again, reducing model size to alleviate gradient scaling was not a part of mixed precision training. Reducing model size sometimes can refer to pruning, but that has no connection with gradient scaling. So between these two values, remember that your gradient values can become very small because you're now going to the FP16 format, right? And those values might simply become 0, right? So you add some scaling factor. Remember that this is like multiplying something and then dividing by it at the end to preserve things, but you have to do the scaling so that these values don't go to 0. If things go to 0, then it's very bad because your model won't converge, right? Everything becomes 0. That's a problem. So these are the two correct answers that are involved in mixed precision training. Let's move to the next question. So by default I will move to the next question quickly for these, but if you have any doubts, please put that on chat. Which of the following are true about mixed precision? Involves only single precision, not possible on the GPU architectures. Mixed precision requires less memory bandwidth. Training with mixed precision speeds up computations by performing operations in half precision format. C and D. Okay. Anyone else? C and D. Okay. Let's take a look at the answers. It is C and D. So let's see why these are not true. Involves only single precision, that's false. As the name itself says, mixed precision, right? So it does involve some computations in FP32 and FP16. So this is not correct. Not possible on the GPU architectures, again not correct, because as you've seen, I think 3 NVIDIA GPU architectures supported, right? Turing, Ampere and Volta. So if this was written as mixed precision is not possible on all GPU architectures, that might be true, because you do need hardware support to implement this, right? And only certain GPU architectures support this. But right now the way it is written, it says that it's not at all possible on GPU architectures, which is false. Requires less memory bandwidth, yes, because your overall data that you need to transfer becomes lesser, and it speeds up computations, yes, because you're doing half precision, right? So both of these are true. Mixed precision is also known as multi-precision, half precision, trans-precision, double precision. C, trans-precision, okay. C, okay. It is trans-precision. So multi-precision is not very true, because it refers to kind of multiple precisions being used, and you know what half precision is and what double precision is, right? From our discussions earlier, I think we had it. So FP16 is half precision, and similarly FP64 is double precision. So by elimination you know that it's not those two. So trans precision is what you're kind of left with, and that is the answer. Yeah, hope this is also clear. How many bits are used to represent the exponent field of TF32? Okay, D, 8 bit. Does anyone else know? Okay, let's take a look. It is 8 bit. So yeah, we have one more right answer. Here is a blog link to TF32 for people who have not seen it. Again, like I said, it was an NVIDIA format. It stands for TensorFloat 32, and this is the FP32 in reference, and you can see the same idea here, right? That, and this is FP16, this is bfloat 16, all for your reference. And here you have TF32, which maintains the same 8 bits but has only 10 bits instead of 23. So it basically has the precision of FP16 and the range of FP32, which is an interesting middle ground to take. So you can read a little more about it from this blog. Dash is required for the gradient value to be shifted into FP16 representable range to match accuracy of FP32 training. Okay, we have answer saying B. Everybody thinks it is B. Yes, it is scaling, like we just discussed, I think 2 questions before, right? Yeah, this loss scaling. So that's kind of the idea. So I think this is also clear. Which of the following is not true about transfer learning? Training from scratch, using learned features from a pre-trained model, sharing training data between different models, fitting a model exclusively to new data without any prior knowledge. Okay, we have one answer saying A, one more saying A, C and D. A, B and C, okay. This looks like a very confusing question to a lot of people. Another one saying A, C, D. Okay, let's look at the answer. It is A, C, D, right? So notice that this says which is not true. So let's look at each of them, right? Training models from scratch is not transfer learning. Transfer learning, as the name itself says, tries to transfer the learned knowledge by retraining over a small set of data. So this is false, right? And since this says not true, you can pick this as one of the not trues. Then B says using learned features from a pre-trained model to train new data. So this is again true about transfer learning. So the not true part is false. So this cannot be an answer. Sharing training data between different models, no, that is not transfer learning, right? There is no notion of different models. It is the same model and you are retraining it on a small new data set which is much smaller. Fitting a model exclusively to new data without leveraging any prior knowledge, again no, you are leveraging the prior knowledge and it's not, therefore it's not exclusively to new data, it is incrementally or retraining on new data. So these two are also false, so they are also not true. So this is the answer for 6. Transfer learning requires more data to train, true or false? False. Okay. Anyone else? False, false. Okay. Okay, it is false. Again, it requires lesser data, right? That's the whole point of it, that you will take just the existing learning and then retrain it on a small subset of new data. So this is definitely false. Next one, which AI toolkit leverages the power of transfer learning to help fine-tune pre-trained models with your own data? C, tau. Okay, anybody else? C, C. Okay, okay, it is tau, as you all have kind of gotten. So we'll move over to the next one. Dash is used to tune a deep neural network to minimize loss and achieve desirable accuracy. Okay, D, optimization. D. Yes, it is optimization. So it's an iterative process that keeps trying to minimize loss, the different forms of loss as we looked at in the previous lectures. and the idea is to achieve a certain accuracy, 90%, 95%, some measure like that, right? So that is optimization. Dimensionality reduction is completely different. How data augmentation convergence technique, just to clarify, is this based on something that was covered in class, or are you generally asking? Generally asking. So I would have to look at what kind of augmentation techniques are typically referred to, but there are so you want your model to basically generalize well. When we say that, we mean that for instance, if I train on, let's say, a handwritten digits, right, things like your MNIST thing, right, where you're writing a number of digits and it's able to recognize those digits. Now let's say you write 4 in a certain way, right? Someone else writes 4 in a slightly different way. This question is from this week's assignment. Okay, I haven't watched this week's lectures yet. And when is the deadline for this assignment again? Week 9, I'm guessing. Okay, I see a 27th, so it's after, yeah, it's next Wednesday, week 8 assignment. Okay, let me take, okay, I have watched week 8 lectures. Let me take a quick look at that. Okay, it's due in a couple of days. Okay. So let's do one thing. We'll anyway, in the recap, we have a little bit about all this generalization error and what techniques are used. So I will go over that, and hopefully that will help you solve the question. But I would not be able to discuss a question for which the deadline is not yet over. That's NPTEL's policy. Obviously, because if we discuss it here, then everybody gets it right? So in case even after our recap today you're not able to understand, then we can definitely discuss it next week. Just remind me next week and we'll talk about it. But today we'll do a bit of recap on all those questions and on all the things that were covered in this week, and you'll hopefully be able to solve it. Okay, so I think we finished this. So last question, state whether this is true or false. Product of scaling factor with the maximum absolute gradient value must be below the maximum value representable in FV16. True. Okay, any other answers? True. 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 Okay, everyone agrees it is true. So you have to basically your maximum gradient value, whatever scaling factor you choose, right, it should be chosen in such a way that the maximum value must be below the maximum representable, because if not, then you're kind of introducing some sort of an error, right, because of the overflow that happens. So that's logically why this should be true. So let's see, we have to go through recap now, but since we are almost at an hour, maybe we can prepone the break and take it now. So it's 7:54. I will see you at 7:59. Feel free to take a quick break and come back. After that, we will do a quick recap of week 8 followed by the questions. Okay, let's continue. So, in the last week, week 7, right, I think we briefly discussed uh, scaling training by distributing it, right? And in that week's lecture, I think there was a brief mention that when you do distributed training, it might affect convergence, right? And why it affects convergence also we will see in some of the following slides. But what can you do for to ensure faster convergence? These are a few techniques: learning rate scaling, ghost batch normalization, learning rate warm up, and certainly optimizers built for exascale deep learning. So let's start with the first one, right? Ghost batch normalization. So first, what is batch normalization? So batch normalization is a technique that's used to increase the robustness and accuracy of a neural network and basically improve its generalization. So what does this do? Many times you might have seen an extra layer saying batch norm layer, right? What this does is it ensures that there is some standard in inputs that are given to a layer across a batch, right? So think of it as some kind of normalization, right? For instance, if you have a certain set of values in many for those of you who have tried simple Python libraries like regression or MLP sort of thing, right, multi-layer perceptron, you will notice that there is always some scaling done before the data is fed into the network. This basically helps increase the robustness of the network. So you will see things like making it zero variance, scaling the data by some factor, and things like that. So batch normalization kind of does the same thing for a given batch. But what is the disadvantage? It uses the batch statistics and therefore it depends on the chosen batch size, right? So ghost batch normalization tries to overcome this limitation. So what it does is it acquires the statistics on small virtual or ghost batches instead of the real large batch, right? And this they have found reduces the generalization error. So this is one of the techniques that you can use to improve convergence. So remember that batch normalization and ghost batch normalization are slightly different. Okay, so next we'll see learning rate scaling. Again, why is this needed? So whenever you use a large mini batch, you need to again think about the convergence and the accuracy because you want to maintain this accuracy, right? So if you do simple data parallelism where you basically you do weak scaling, right, you don't reduce the per worker workload, you keep that the same, your overall batch size increases like we saw in the weak scaling slide. Okay, that was a good number of slides back, but let me just go there so that you get a quick recap. So this, right, so you see that the effective batch size increases. Now this causes some convergence issues. Again, why is this? If you want to understand that a little more, you can look at this whole gradient descent short videos like the one I had put for momentum, right? So you saw that ball rolling towards an optimum, right? So you can visualize the same thing on the internet. If you do a quick search, you should be able to find it for different batch sizes. So that will give you an idea of why convergence is an issue with larger batch sizes. But that is basically the problem we are trying to address. So how do we address it? By using a linear learning rate scaling. So basically when you multiply the batch size by k, you multiply the learning rate also by k. So this is called a linear scaling rule, and this is found to be effective for a broad range of mini batch sizes and all other hyperparameters. So remember that the learning rate is also a hyperparameter. The other things are kept unchanged. It's sufficient to just increase the learning rate whenever you increase the mini batch size. So this is the second technique for convergence improvement. Okay, so next is the optimizer part. So again you will notice here that there are some specialized optimizers. For instance, this says Lars, and you can also see the no Lars in contrast, and you can see its test accuracy never actually reaches this, whereas these two are batch size 256 and batch size 16,000. So with Lars, which is a custom optimizer, you can see that the 16K batch size is able to reach the same accuracy of 256, right? Meaning that your large batch size issues are no longer there. But if you don't use Lars, you see that the accuracy drops, right, which you don't want. And you can see that here also. So this is the effect of optimizers for deep learning. Okay, so that is one part of it. Now I think we move to the second half of it, right? So the first half of your week 8 was challenges with convergence. Now we move over to the inference part of things. Before that, are there any questions on this? Anything that's not clear? Nothing? Okay. If not, let's continue. So again, training is only one part of the story, right? You also have inference and deployment, right? So what do we mean when we say deployment? So what is inference? First of all, once a model is trained, it has learned some things. Now we'll actually use it to make predictions or decisions, right? This is called inference. For instance, a simple example that I'm sure all of you have seen is to do a cat or dog prediction, right? So your model tells you that I'm 90% sure this is a cat, right? Or you might use something like YOLO, which detects a certain object with a certain confidence, and will also give you a bounding box. So these are all examples of inference. Now when we talk about deployment, we mean where is this going to run, or where are we going to deploy this. So for instance, one option could be edge devices, which you'll study a little more in detail in the coming weeks, or you could do it on the cloud, right? I'm sure some of you have used things like Colab, or you've heard of AWS and various other Microsoft. For instance, Microsoft's cloud offering. You would have heard of various companies and their cloud platforms, right? So all of those are choices. So where do we deploy it is a question. Then finally, once you deploy it, how do you measure the performance of this deployed inference system? So that is broadly what we are talking about, and this shows you the workflow. So training is, first you take a model, you have a framework like PyTorch or TensorFlow, you give some data set to the model, and the model learns something. So this, at the end of the training, you have a model with updated weights, right? Now you take the same model and you give it some new data, which you might get from a real-time sensor, or you might use some other data, that doesn't matter. You give it to this trained network, and then it will give you some outputs, and this is typically optimized to be very performant. This is the whole pipeline. Now when we talk about performance, what do we mean, right? We can mean several things. First one is accuracy. Obviously the first thing you care about is how accurate the model is on the queries that are coming in. For instance, if I ask you, is this a cat or a dog, and you tell me that you tell me the wrong answer most of the times, then this is not a very accurate system, right? So we measure that accuracy, first thing. Second thing is latency. Between me asking a question and between when you get a prediction, how much time does it take, or how long do you have to wait? This is also a very important thing. For instance, in user facing things, for instance, you ask ChatGPT a question, and sometimes you might notice that it takes 30 seconds and then says that it timed out, or there is a network error. Then you're very unhappy with it, right? And in other cases, you might be using this model to do inference in a very real-time system. For instance, you're driving on the road and you're kind of in an autonomous vehicle where you're not actually using the steering. So there is logic inside the edge device in the vehicle where it detects what is there on the road and accordingly makes decisions. Now if the detection itself takes a lot of time, then the decision is not going to be in real time and you could end up with some unwanted consequences like an accident, right? So latency is also a very important thing. Now next is throughput. If I have a large batch of queries, then how many predictions can I get per second out of the system? So again, remember the difference between latency and throughput. If you don't, go back and look at that live session. It's in hybrid. Okay, hybrid, I'm assuming you're talking about this cloud versus edge. Yes, you can have a hybrid scenario where you do some part of the work on edge, offload the rest to the cloud. Things like that are also done, and that's also a valid deployment scenario. If that didn't answer your question, please ask me again. I'm hoping that was the question. Okay, other metrics that we can use is energy or power. How much energy is consumed? Okay, that answers it. Great. How much energy is consumed to make one prediction? How much power is used by the system? All of these can be considerations, right? For instance, I can put an edge device in a very remote location and I can have a power bank powering it. So then all of these things become very important. Then there is also model size. How many bytes are needed to store or transmit the learned model? How much memory is used by the deployed ML system? For instance, if I want to run something on a Raspberry Pi that has 4 GB of memory, then how much memory this uses becomes very important. And finally, there is cost. How much money does this deployment cost? So all of these are valid performance metrics. You might use one or more. Typically it's a combination of accuracy and another time metric like latency or throughput. Energy can also come into play, right? So multiple metrics can be of interest at the same time and you kind of try to get the best possible outcome. But in general, all of these are performance metrics. Okay, so deployment is basically kind of integrating it into an existing production environment, which takes an input, returns the output. Why is this important? You need to effectively deploy it. Only then can you get proper prediction. When we say proper, again we are referring to some of these metrics. How much time does it take, for instance, can vary depending on whether I run it on the cloud, you see AWS here, or I run it on a local GPU, or I run it somewhere here, right? I'm assuming EI stands for elastic inferencing. So all of these choices can make a difference. So that's why deployment is important. Okay, so now given that we saw some memory constraints and some model size constraints, right? One obvious optimization you can think of is, can I make a model smaller? If so, how do I do that, right? So this is broadly like compression, right? So you would have heard of image compression, video compression. You will see popular messaging platforms like WhatsApp taking your images and compressing them, right? So that even in a low bandwidth network or a low speed network, you're able to send it as quickly as possible. So similarly, we also want to do model compression here. Basically, you want to have a smaller, easier to compute network, but without too much of a compromise on accuracy, right? So one option is to use low precision arithmetic. So for instance, you might see things like integers, int8, int4, variable precision integers being used. So that's one way to go about it. The other thing is to do pruning, which is removing weights that are close to zero, removing activations that are close to zero. This also creates a smaller model. So this is one more approach. Then you have information theoretic approaches, which are based on your very classic techniques like Huffman coding, and these are referred to as lossless compression techniques. So you could also do this where you compress at one end, then you decompress at the other end. Then you could do something like knowledge distillation, where you have a large teacher model which trains a smaller student model, right? This is called knowledge distillation. then you could come up with better architectures that are edge or mobile friendly, which are suitable for inference. For instance, MobileNet, ShuffleNet, lot of these are made to be very inference friendly. So all of these are ways you can make a model smaller and get better performance. So here is an example of inferencing at low precision, right? So here again we are comparing FP ranges with integer ranges. So notice the difference. FP16 goes from 65,000 to plus. This goes from minus 128 to plus 128. Now what are the advantages of switching to int from FP32 is you first of all reduce your storage and therefore your bandwidth, and integer compute, like we discussed a long time ago, is a lot faster than floating point compute, and that also saves you energy. For instance, an integer add operation results in a 30x energy saving and a 116x area saving. I don't remember what the area is about, but I'm assuming it's the chip area itself, right? For your floating point hardware versus your integer hardware. So if you could do away with your floating point hardware unit entirely, you would save on this much area and also power and energy, right? Similarly for multiplication. So here you can see the top 1 accuracies compared for different models across FP32 and int8, and you can see that the difference is barely noticeable. It's 0.5% or 0.6% at worst, right? So you could do inferencing at low precision very easily and get good accuracies. That's what this tells you. Are there any other questions so far? I think TensorRT is the last part we have in the recap. Okay, if not, so what is TensorRT? So far we've studied things like PyTorch and TensorFlow, right? TensorRT is kind of a framework, but from NVIDIA itself, and it's intended to accelerate inference, right? So it's intended to make inference as high performance as possible, deliver very low latency and high throughput inference for deep learning. So how does it do this? We will see. But what does the pipeline look like? So you get a neural network, right? You train it using whatever, maybe that's PyTorch, maybe that's TensorFlow. You get your neural network. Now you give this to TensorRT, which will optimize it. We will talk about this optimizations in a little while, but it optimizes it and generates something called a plan. And this plan can be serialized and stored to disk, and or you can directly validate it using TensorRT and run it, right? So this is in TensorRT is purely for inference. It cannot do training, and it is intended for NVIDIA hardware only, right? It's released by NVIDIA. So why should you use TensorRT? First of all, again, it's high performance, and it processes things faster. So these are all very high level things, right? Up to 40x faster, deploy to hyperscale data centers, embedded or automotive product platforms. It can deal with recommendation, speech, video, translation, takes advantage of the entire NVIDIA suite of tools, and it's compatible with all of these edge devices, right? So that's the high level overview of why TensorRT. But how does TensorRT do better, right? You could do inference using PyTorch or TensorFlow also, as you saw. So what does TensorRT do specially? So first thing is reduced precision or precision calibration. As we already saw, you could do FP16 or int8. Both these options are available, and TensorRT does this while preserving accuracy, right? So this basically reduces latency and reduces model size, and that's one benefit you get. Second thing it does is something called layer or tensor fusion. So let's say I have 3 layers that look like something like this, right? Now TensorRT is kind of it kind of let's say there are multiple nodes in these layers, it fuses these nodes into one single node, right? You can't do this for every single layer, but there are some layers where you can do this. For instance, layers with unused output are eliminated, then layers where convolution, bias and ReLU, so basically all of these are fused into a single layer. So there is a figure, that shows you this. So this is what the unoptimized network looks like. So as we saw in the previous slide, this set of layers can all be fused, right? Wherever you see this ReLU, bias, convolution. So therefore this whole thing starts looking like this now. What is the advantage of doing this? It optimizes the use of GPU memory and bandwidth. So that's another thing that TensorRT does. Then it also auto tunes the kernel. So remember that it's an NVIDIA specific tool, right? So it has some knowledge of the target GPU or the underlying hardware, and based on that it will pick algorithms and data layers suitable to that target hardware. So it has this library of kernels that will kind of give you the best performance for that target GPU, input data size, etc., etc. So it will pick that performance. That's another, it will pick that algorithm or that implementation. So that's another reason why you get a performance benefit. Then there are some other things like dynamic tensor memory, multi-stream execution, time fusion. You can look through these, but you don't need to know them in detail. So we'll skip them for now. So this is basically all of these put together in one picture. So we already saw this. It takes a trained neural network. It performs all of these optimizations and gives you what is called an optimized inference engine. So what does deploying a model look like with a TensorRT? So you have a trained neural network. You import this model into TensorRT's into the TensorRT framework. Then the optimizer does a bunch of things on it, and remember that there is an inference engine that's generated. Now typically this inference engine can be stored to disk, right? And then when you want to run it, you again take it from disk. And this is like a plan, right? So you take that plan and you load it or you deserialize it, and then you give it to the TensorRT runtime engine, and that's how you finally deploy it or you run it, right? This is the whole flow. And since this is something that NVIDIA gives you, it's not as full-fledged as PyTorch or TensorFlow. So there are only some layers that it supports because it does a lot of these optimizations. It picks implementations that are written for that hardware. There is a trade-off, right? The trade-off is that it doesn't support all possible layers. It supports basically these, and these are very commonly used. So if you try to implement something that's outside this using TensorRT, then you may run into issues. That's something to keep in mind. So with that, we come to the end of the recap. So any questions so far? So what is quantization? So basically it is this low precision thing that we were talking about. Quantization, I think, specifically refers to integer, not FP16, refers to integer. And again, depending on what hardware you have, right, you can have arbitrary precisions also. For instance, on FPGA you could have int4, int3, int2 and things like that. On standard hardware, int8 is what the hardware supports, right? So that's what makes sense. So quantization typically refers to integer lower precision, not floating point, from what I remember, and that's what TensorRT also refers to. So int8 is what you can think of as quantization with TensorRT. Any other doubts? Okay, final exam would typically be very similar to your assignment question. So go through all of the assignment questions so far, go through the live sessions, and that should help you kind of prepare for the final exam. I don't think there are any non-MCQ type of questions. So doing all of these properly, again the questions won't be the same, but as you can see they are very similar, right? So you will have very similar questions in the final exam also. So going through both of these should definitely help you do well in the final exam. And there are no numericals in this subject, right? At least so far we haven't seen any. So it's fairly easy, but it can also be a little difficult because sometimes you might be asked things that are not directly covered in the lecture. So that's why the other thing I suggest is whenever you see options that you're not familiar with, for instance in this, so far in the questions that we discussed, right? Here for instance you see 4 options, maybe you know what tau is because that's the answer to this, but you don't know what is NVML or you don't really remember what are these things. So I would recommend going immediately looking them up and making a note of them somewhere so that you can quickly revise that before the final exam. Typically sometimes different questions are made and which might have one of these options as the question, right? So you can either, knowing this extra information will help you quickly eliminate the wrong options. It could also help you identify the right answer, right, depending on the question. So that's one thing I would suggest, because in a theoretical course you don't have numericals to ask, so it has to be a theoretical question and it can't be the same as these questions. So many times there will be variants that are asked. So knowing a little bit extra apart from what's taught in the course will help you get a very good score. So that is something I would recommend. Any other doubts or questions? Hope that answers your question. Sure, no problem. And for an older course, I would have also recommended watching last year's live sessions, but I don't think there are last year's live sessions for this course, so this will be it. And the previous year's assignments are anyway what I'm discussing in the live session. So if these are kind of all the possible questions for this course so far, but that doesn't mean the exam will have the same question. So it will be something slightly different, but this will definitely help you prepare. Okay, with that, let's transition into the questions for today. Which of these optimizers are most commonly known to solve convergence issues for large-scale distributed deep learning? Conjugate gradient, Adam, LAMB, all of the above. So this is one of the examples that I was talking about, right? You might not have heard of all of these optimizers in the class, but it is something that's asked. So now you have to kind of figure out how to answer it. So these kind of questions, a few will be there in the exam as well. Okay, we have one answer saying C. C, okay. Any other answers? Let's look at the answer. It is LAMB. It stands for Layer Wise Adaptive Moments Optimizer for batch training, and there is an explanation of this in the blog post. Again, I don't think, Adam, you might have probably heard from the previous lectures. Conjugate gradient, I don't know if you've heard of it, but it would be a good idea to look into this. And like I said, whenever you do this, you don't need to know a lot of details, right? Just try to write one line about it based on whatever you read. And again, things like Towards Data Science are all very easily accessible websites, right? For the most part, Geeks for Geeks, things like this are intended for undergraduate students. So refer those for your first cut understanding of what these are. So LAMB is one of the ones that is used to solve convergence issues. Okay, next question. which shows the relation between batch size and learning rate. You have 4 options. Take a minute to look through this. Okay, we have one answer saying D, one more saying C, one more saying D. Okay, one more saying D. Okay, let's look at the answer. It is D. When the mini batch size is multiplied by K, multiply the learning rate by K. So, if you remember in the very first slide where we spoke about this learning rate scaling, this is the linear scaling rule, right? So, what it says, what is the problem here? When you have large mini batches, it affects your convergence and accuracy. So, what you try to do to compensate for the increase in batch size is to also multiply the learning rate. So it says when the batch size is multiplied by K, multiply the learning rate by K. So that's what you do here, and because of that, option D, which says both are multiplied by K, is true. This one is inversely proportional. But if you really want to understand why this is, right, I think it would be good to look at even SGD, right, stochastic gradient descent, versus batch gradient descent. These are two extremes that you have, and in between is your mini batch gradient descent, right? So this itself, the convergence curve, what the accuracies look like, right? That will tell you a little bit more about how this whole gradient descent works and how the mini batch works. And it will help you understand this part. The batch gradient descent will help you understand what issues you have with large batch size. And then you will be able to connect the dots on why increasing the learning rate helps you with this. So if you would like to understand this better, let me know and we can discuss it in the next class. But that's optional, right? It's not really necessary for the course. So it's purely out of your own interest. If you want to understand it, then I can spend some time talking about it. But let me know on chat. Okay, let's move on. Among the following, which of these are considered as a measure of performance of the deployed system? So you have A to G and you have various combinations of those. This is again something we discussed, so think about it. D, all of the above, okay. A, which is everything except E, memory use, okay. Anyone else? D, all of the above, okay. Yes, it is D, all of the above. Again, this is directly from the slide, so I don't think it will be too difficult. So look at this, right? It's exactly this. How do we characterize the performance of a deployed system? We use metrics like accuracy, latency, throughput, energy or power, model size, memory use, and cost. So all of those were your options: accuracy, latency, model size, throughput, memory use, energy, cost. So D, all of the above, is the correct answer. Let's move on. Which of the following is not a model compression technique? Low precision inference, pruning, tuning, knowledge distillation. Any answers? C, tuning. Okay. D, knowledge distillation. C, tuning. Okay. Okay, let's look at the answer. It is C, tuning, which I think most of you have gotten right. There was a little bit confusion, so let's talk about this. So what does low precision do? Right, it changes the weights and activations from FP32 to either FP16 or int8. So in a way, the weights are being compressed. The precision is being compressed. So you can think of this as a model compression technique. Similarly, pruning removes certain things, right? Let's go back to pruning. Where was that? Yeah, pruning. So you remove some weights that are close to 0 or activations that are close to 0. So this also creates a smaller model. So when we say compression here, we are basically referring to creating a smaller model. So pruning also does that. And lastly, we spoke about knowledge distillation, where you have a teacher model and a smaller student model. So the teacher model kind of trains the smaller student model. So again, it's a way of distilling or compressing the model. But tuning is typically kind of fine tuning the weights of the model. It's used in that context. So that's not really making the model smaller, right? So in that sense, these three are compression techniques. This is not. So the answer is C. Let's move on. Which of the following is true about TensorRT? Inference optimizer, low throughput, released by NVIDIA. And you have 4 combinations. Okay, we have one answer saying A, comma C. Okay. Anyone else? I'll give you one more minute. A. Okay. A. Okay, let's take a look. It is A. It is an inference optimizer, as we discussed. It is also released by NVIDIA. Low throughput is false. If you remember, it says low latency, high throughput. So again, try to keep the definitions in mind, right? What does latency mean? What does throughput mean? And for any metric, you should have this idea of higher is better or lower is better. Let's say we are talking about, I'll give you examples for this, right? So it becomes easier. Accuracy. So if let's say we are talking about like a percentage accuracy or a top 1 accuracy. So what is better? Higher is better, right? 95% accuracy is better than 50% accuracy. Latency, lower is better. If you have to wait 10 seconds versus waiting 20 seconds, 10 seconds is better. Throughput, higher is better. The higher number of predictions per second you can get, better it is. Energy or power, lower is better. Model size, lower is better. Memory use, lower is better. Cost, memory, lower is better. So this is kind of how do you think about what is better in terms of a metric. So that way, if you think of throughput, higher is better, right? So any framework typically that tries to give you best performance for inference will also try to give you high throughput, low latency. So that's one way to answer this. The other is to kind of also come up with these two and see what options you can get with A and C, and that kind of eliminates B and C for you. So you either have A or D. So you still have to think about this, but if you know the definitions of throughput and latency, I think it's easy to figure out, even if you haven't read this about TensorRT or you don't remember it exactly. Okay, let's move on. Any questions so far, friend? Questions 1 to 5? Any doubts? Something that's not clear? Something that you would like to learn more about? feel free to ask. I'll give you 30 more seconds. Think about it. Okay, there are no questions. Let's move forward. Which feature of TensorRT maximizes throughput with FP16 or Int8? Time fusion, reduced precision calibration, auto tuning a kernel, dynamic tensor memory. B, reduced precision or precision calibration. Okay. Anyone else? B, okay. Okay, let's look at it. It is reduced precision or precision calibration. Auto tuning. So again, look at what the question asks, right? Which one maximizes throughput? So auto tuning a kernel is again something that TensorRT does, and it also maximizes throughput, but it does not involve FP16 or Int8. Similarly, if you looked at fusion, I'm not sure what time fusion here refers to, but you've looked at kernel fusion or layer fusion. Again, that does not deal with FP16 or Int8. Same goes for dynamic tensor memory. And if you remember what reduced precision is, it involves exactly this FP16 or Int8, and because of that you get a higher throughput. So this is a feature that gives you this and uses this. Question 7. Dash is the maximum batch size above which scaling efficiency decreases significantly. This we did not have in our recap, but maybe you remember it from your slides. Okay, critical batch size. Anyone else? Okay, same answer. Okay, let's look at it. It is critical batch size. So it was from this slide, right, where you're shown various batch sizes and a gradient noise on the y-axis. And critical batch size is basically a threshold. It's the maximum batch size above which your scaling efficiency decreases significantly, meaning that even if you increase the batch size, you don't get that much of a benefit. So that's your critical batch size. Dash is a technique to remove redundant or unimportant weights from DNA. So there are some questions without options in this week. Again, keep this in mind for the exam also. You might have some questions like this. Pruning, okay. Anyone else? No one? Okay, I think you guys might have forgotten. So it is pruning. So let's go back to that slide. I didn't put it since it was here. But yeah, this is the definition of pruning, right? You remove weights that are close to zero and activations that are zero. And you make the network smaller. So this is what the question is asking you about. Remove redundant or unimportant weights from the DNN. The answer is pruning. Let's move to the next question. Dash is a process of transferring the generalization ability of the cumbersome model to the compact model. It's worded a little differently, but hopefully you're able to remember. Any ideas? Ghost batch normalization. Okay. But think of this part particularly, right? You're trying to, maybe cumbersome is kind of a bad word. Let's say a larger model to a smaller model. We looked at this definition particularly. Inference, not really. Batch norm, okay. Anyone else? Think about it a little more. So do you have two models involved in batch normalization or ghost batch normalization or inference? Here you are particularly talking about two models, right? In the context of that, does something else come to mind? No? Okay, let's look at it. It is knowledge distillation. So remember, we spoke about a teacher model and a student model in the context of making your model smaller, right? In this part. So take a large or a complex model, which is called a teacher, and train a smaller or simpler one called the student. So here I think the terminology was slightly different, so maybe it didn't come to mind. But that's essentially what knowledge distillation is. So you want the smaller model or the more compact model to do what the larger one is doing, right? So that's knowledge distillation. Dash is known to accelerate training, increase robustness of neural network to different initialization schemes, and improve generalization. Batch normalization. Any other answers? Anyone? Normalization, batch normalization. Okay. It is batch normalization. So if you go all the way to the first recap of today, right? We spoke about batch normalization. We have exactly that, different initialization schemes, and the idea is to improve generalization of the network. So that's the idea behind batch normalization. So with this, I think we come to an end of the questions for today, and we have 10 minutes. So we'll take 2 minutes maybe. If you have any questions or doubts in any of the 8 weeks so far, please ask, and then we'll end early because I know it's a holiday for many of you, maybe today or tomorrow. So It's nice that you guys still joined, but you can go, you can drop off early. So in case you have questions or doubts, please ask, because there are only 4 live sessions left, right? So it's good to start getting your doubts cleared as early as possible. And if you want any week's assignment questions discussed, right, that also can be a request. Like we did week 6 today, we can also do some other week next time. So feel free to ask whatever it is that will help you the most. I'm happy to do that, because I think soon after the 12th live session, it will kind of get to the exam. So learning rate higher is better. Um, that would again depend. It's again a hyperparameter. So maybe I'll take some time to answer this, right? Let me look it up and see under what constraints or conditions it's better, and what conditions it can be worst. So I'm not very sure at this point. But I will get back to you in the next session. Any other doubts or questions? Are things getting clearer as you listen to the lectures and finish the assignments? Or do you still feel that the course is very tough? You're welcome. Thank you for attending. And if you have no doubts or questions, feel free to drop off. I'll just hang around for another minute or so to see if there are any other questions. If not, thank you so much and look forward to seeing you next week. Oh yeah, you will get access to the notes in the form of slides. I'll just share the drive link here again, but you can use this for the slides. This will have a PPT uploaded for each week, and you also have the YouTube channel for the recordings. So you can watch it or download it in whatever form that works for you. And I typically upload with any notes or any things that I've done during class. So if you want that also, that's available in the slide that's uploaded. Hopefully that's helpful. If you need anything else, please feel free to ask. Sure, no problem. Any other doubts, questions, comments? Are these live sessions helpful? Would you like more of a certain thing, for instance, more questions, more recap? We can change it however you think would be helpful. More recap? Okay, sure, we can try and do that. I think today was a little shorter. One reason is the content itself was less this week. We had 3 videos instead of the usual 5. Second reason is, again, I think someone wanted a previous week's assignment to get discussed, so accordingly I made the slides. But next week onwards, I think we'll have more of recap anyway. I think this week there are 6 or 5 videos, so we'll definitely have a lot of recap. Okay, anything else before we wrap up? Okay, if not, thank you all and see you next week. Bye.